Live. So welcome to, well, you're in the thick of it, you know. You've got the last exam coming up on Monday, and here we are. One last topic, and it's a banger. We have the trigonometry in 3D, but it's exact values. This is a very important debate in maths about what an exact value is. And we'll preface this with that debate. So today we're looking at live session 16. 3D trig and exact values. There's nothing much more to 3D trigonometry than there is 2D, except your ability to conceptualize it in 3D and draw out where that triangle is. And sometimes a diagram can be invaluable. We'll look at the exact values. We'll look at exact values in 2D and also a bit in 3D. Remember, these are not like hundreds of questions. It's meant to be short, snappy, and get you back in the driving seat for this topic. Okay, so there's 4 days to go till exam number 3. And if you've got any questions that you want, make sure to put them in the comments below. You know, it's last minute. You may have some worries. No worries. Don't worry about that. Get those questions off to me. Happy to reply with all my experience, and if I don't know, I'm 100% sure I know someone that does. So don't suffer in silence there, eh? Okay, where are we at? The conversation around exact values. So if you type in your in a calculator, let's say 3 divided by 7, and you get, let's write that down so you know what I did, 3 divided by 7. And it's 0.428571428 and it keeps going. And it's not very nice. You could also type in root 3. And root 3 is, obviously we press STD button, 1.73205. I do not remember these on the top of my head. This is using a calculator. And let's write it as a fraction. What I highlight here are the exact. Okay, so these are the exact. And what makes them exact? Well, the numbers in decimal form will go on and forever. Okay, and they'll never stop. Essentially, if I took this first one to 1 decimal place, that's 0.4, what would that look like? If this is 1, and let's say that's 0.5, 0.4 would be about there. That's what that number is if it was 1 decimal place. If this number was 2 decimal places, 0.42, well, that's a little bit more than before, isn't it? It's about there. So already, if we only accepted the 0.4, we have a number which is a little bit less than its true form. Let's go a little bit more, 0.428. So that's something so small in terms of addition that I can barely write it. So I can't go past 0.5. But you get the idea that every little bit, every extra number, 8 and 5, every extra number is a little bit more on top. And this goes on forever. So that's a lot of forevers. Now, if you look at it, it's never going to go past the decimal that came before it, right? So you're never going to get 0.5. This number is never going to hit that. This number is also never going to hit 0.43. because it's 42 and something. It's never going to hit 0.439 because, or 429, because we have the 8 there. And so there's a limit to what this number is going to do. It's going to converge. It's going to keep getting bigger to a point, and then it's going to taper off. And eventually, I mean, we might call it an asymptote there. Something that it will never reach, but it keeps going up very slowly, and the more decimal places, the smaller it is, and etc. So it might converge to a point at some point. But all of that is going to be, all that accuracy of where it's headed is going to be lost if we cut it off early. And so that's the main reason that we don't use decimals very much, because no matter what, if you cut it off, you missed out a lot of, well, it's not a lot of accuracy. You've missed out a lot of numbers. You've missed out something which some people might consider too small to care about. So in that case, maybe you don't care about this, and you could use 0.42, because for most of what we do in our life, you don't need much more, and if you're rounding it. But if you did want the exact answer, using 3/7 is actually, look how elegant that is, how easy it is to just write 3 divided by 7. It doesn't seem to be onerous. So I think you should really get used to using fractions. This would be an example of an exact value versus a decimal. And with the root 3, that's even easier to write square root 3. And it's an example of an exact number versus the decimal, which is always going to be rounded. And it brings up a debate. If I didn't care for using these exact values, which I really would argue that they're a lot easier to deal with than decimals, then what accuracy should I work to? Well, if the question asks for you to give your final answer at 2 decimal places, most of your answers, you should cut them off at 4 decimal places to be sure. Now, it depends on how many calculations you're going to do, because every calculation that you introduce is going to increase the error away. So if I used let's use an example up here. I used 0.42 in my calculation. Let's say we were doing 3/7 squared, and then I multiply it by 0.42. I've now got 2 numbers that have been rounded. So I've done essentially 2 roundings, and the result that follows from this is a lot further away than when it began with just the difference of cutting it off. So if I do 0.42 times 0.42, I'm at 0.1764. And comparing that to 3/7 squared, and 3/7 squared is actually, let's get rid of some of this. It's actually 0.18367. So by rounding it before the end, my answer is kind of bad. If I rounded it to 2 decimal places right now, I'm 1 out. And the examiner might think, oh, we got that wrong. So we miss out on an accuracy mark. Not ideal. However, if instead we pick 4 decimal places, so 0.4285 squared, that's times by itself, then we get 0.1836, which is going to be enough if we rounded it to 2 decimal places to be the same as if we'd used the full number. So you just need to use an accuracy a couple of decimal places longer than what your intention is going to be. Nice and clear, I hope. So it underpins the whole point of exact values. So really worthwhile having that conversation just to make sure that that was not the thing holding you back for why we bother with this. And I could argue a lot about how fractions are so much easier to work with than decimals. Like leave your answer in fraction form. I'm actually get really excited about that because there's less to mess around with. Decimals can get messy, but also take a lot of time. Let's look at some of these questions, Find the value of x in the following triangle, leaving your answer in exact form. So when it says in exact form, it means we don't want any decimals. Now in the old days, your calculators, and maybe you've still got one like this, your calculator would only give you in like decimal form. So here, using a calculator would not give you an advantage. The calculator would give you decimal Okay, that's the old days. These days, if you've got the Casio, this is not a plug, by the way. I don't get any money for this. I'm just a big fan. Casio FX, 991EX, it is an FX, but I don't need to write it. This calculator, and a lot of them the same range. So what's the other range? The 991ES and the CW, all of those, they'll give an answer which is exact. And therefore, you don't need necessarily to worry, like is it a calculator exam that I'm going to have to be careful and not be able to use my calculator? In the modern one, it gives you an exact form. The tough part is having to show your work in as you go through. If you're just writing randomly down and you literally have to show, and it says in the question, show clearly, then you're going to have trouble. Unless you fully understand the method without a calculator. So I fully endorse not doing this live stream and these set of questions using a calculator, but to think for yourself and go through that process, because going through that process yourself, that is really important for your journey. And I'm a big believer in this. I'll talk some more on the topic, mainly around what exactly I would do. Yeah, so what I would probably, I'm going to make a statement when it comes to using calculators that thinking can't be outsourced to other things. You stop using that brain, you're going to lose it. Okay? In my opinion, what we're doing here is a journey of self-discovery. Okay, we're learning our extent of our relationship with the universe through the medium of numbers. And you know, we need to take ownership of that. We need to walk those steps ourselves. And if we're going to outsource it because we're tempted by what's easy, we're going to miss out on something very valuable. And when there's not enough time, I feel like, to heal the traumas that we've experienced in the math classroom in younger ages, and we don't have the time to have authentic learning experiences because the curriculum is shoved down our throat, or we've lost time, or whatever it is, then in the place, and it could also be the laziness, because we could think, I just want an easy ride and we're not going to make the effort, we're not going to show up for ourselves and others. What we end up experiencing instead is a bunch of tricks and misconceptions. And then what we have for our experience in life is very much dulled. We don't fully appreciate it, and we end up with misconceptions. And if you act in life based on false information, and and you come to conclusions which don't follow one from the other, it can be very frustrating from a philosophical standpoint. I'll let you think about that and expand it in your own time. But back here is the reason why it's not a bad thing at all to do exact form without a calculator. And if you really must use a calculator, use it to double check what you're doing. Okay, let's get started. This is the health warning out of the way. So this works exactly like it does with others, but we need to appreciate the fact that certain angles are going to be nicer to work with without a calculator. So the angle involved in this question is 30 degrees. And this is where your warning sign goes off. Warning siren goes off in your head, because 30 degrees is one of those lovely angles. Now it is time for a mini lesson, aside from all of this, for people that want to know where this comes from, like why are these angles particularly good. So if you're ever in the exam in a situation where, I can't remember what they are, because you can remember them as a table. So we're eventually going to, how should we set this table up? I suppose we could do it like a table. This is a very off the cuff. So let's just say we've got tan, sine, and cosine. And the angles of special notoriety are these three. And that's because these exist in very special triangles. Triangles that we can know everything about, and therefore we can write statements about these values. So if we want to find tan 30, what is that? Well, typically if you put tan of anything in a calculator, you try it now if you want, tan of 32, and for those that don't have a calculator, it's 0.62486. It's not very nice. Typically that's the case. However, if you type in tan 30, it's actually really nice. It comes to be this nice expression, whereas all the others, it can't be written like this, but this one can. That's the same with all the others. Tan 45, for example, is even nicer, as we've probably remembered. It's 1. And as you can see, there are 9 facts to remember. If you're someone that works based on memory, then you can remember this with, pretty much with ease. And whenever the question comes up, you can say, oh, I remember what that value is, and you can replace it, and then away you go. This is a brain, by the way, for representing memory. A little bit more wrinkly, isn't it? Or if you're a person that likes to use what we call first principles, it means that you understand like principles and ideas at a base level, and you build up from there to understand the more complex ideas. This sort of approach, what we're about to do, is how you do that. You draw a triangle. So as we were talking about before, they come from triangles. The first triangle that we want to draw is the equilateral. And in the exam, I often draw these. You get really quick at it. But this equilateral, and trust me, we're going to label the sides 2 rather than 1. Like, it doesn't matter whatever number is easiest, but trust me with a 2, because that will help us get rid of a fraction later. I'm going to get rid of these, so not too complicated of a diagram. What do we know about the equilateral triangle? Well, the beauty of it is that all of these angles are 60 degrees, right? We know all of that. And since we're dealing with trigonometry, we need a right angle triangle. So how do we get that? We drop down right from the middle there. So we suddenly now have a right triangle. What's the angle up the top? It's half of the 60. So we still know all the angles. And if we focus on the triangle on the left, we have all the angles. Do we have all the sides? Well, this drop here is actually a perpendicular bisector. This is exactly half. If I write both sides there, it makes it easier to understand that I've halved it. So we've got this bottom length. We've got the 2, which is hypotenuse. Oh, I don't know if I'll be able to move that, actually. Just rewrite it. There. And what we'd like to know is this one. And we can easily find that with Pythagoras. So we are pretty fluent with Pythagoras at this point, hopefully. So 2 squared minus 1 squared, that's 4. Take away 1 and square rooted, so that's square root 3. And that works because we changed the equilateral triangle to 2. You imagine doing that if it was 1, you'd have a bit of a fraction on your hands. So you can thank me later. There. So we know everything about this triangle, so we can write facts about this triangle. So let's focus on the facts that we can write about an angle of 60, right here. So what is 60? Let's talk about the ratios and write them at the top. So sine theta equals the opposite over the hypotenuse. Cosine theta is the adjacent over the hypotenuse. And tan theta is equal to the opposite over the adjacent. So if we want to know what the exact, like a value, a nice value for sine of 60, okay, we're going to do the opposite, which is root 3, divided by the hypotenuse, which is 2. So sine 60 is root 3 over 2. That's an exact value. And if you're uncomfortable with it because it's not 10 or 3.5, and the fact that it's a fraction or that it's got a square root, then I suggest you make friends, because it's a really lovely way of writing it, and rather than all of the other decimals or even using a calculator. Which, by the way, if you've not got fractions sorted at this stage, you should be super 100% comfortable. They are the fundamental of learning GCSE, even preceding quadratics. Definitely, actually, preceding quadratics. If we look at it again, we've now got 60 degrees. Let's fill out another one on that bottom row. Let's do cosine. Cosine is the adjacent over the hypotenuse, so that's 1 over 2. Nice and easy one. Tan is the opposite divided by the adjacent. So that's root 3 over 1, so that's just root 3. See how easy this is? We can fill out the top row now, because we've got 30 degrees along the top, right here. So from this viewpoint, tan is the opposite over the adjacent, so that's 1 over root 3. So tan 30, 1 over root 3. Sine is the opposite over the hypotenuse, so that's its turn to be a half. You'll notice that some of these values are coming back again. Well, they must do, because we're using the same triangle 3 times for each one, right? So cosine is the adjacent over the hypotenuse, so look, they switched around. And that's actually a good observation. Sine and cosine of 30 and 60. You see, when they're using complements up to 90, they're going to be like reversed. So sine of 30 is the same as cosine of 60, because 30 and 60 are the complement to 90. And you'll notice cosine of 30 is root 3 over 2. So we would assume that sine of 60 is root 3 over 2, and it is. All right, now on to the next triangle. So that's all we're going to get in terms of angles out of this one. Our next triangle is an isosceles right triangle. What's an isosceles right triangle, you ask? Well, let's look. Isosceles means two sides are the same. That's this one and this one. And the right angle is there. So if we just arbitrarily say this is side 1 and this is side 1, because it doesn't matter what side it is, like it's all going to be relative to each other, then we can use Pythagoras. 1 squared plus 1 squared square root equals root 2 to find all of the sides of this triangle. Your next question is, do we know the angles? Well, if this is 90 and this is an isosceles, then the rest, these two must be the same, and there's a remainder of 90, so they must be 45 degrees each. Now we know everything about this triangle. Beauty. And we're going to see what we can find in terms of facts. It doesn't matter, they're both 45, so let's pick this one. No, different color, eh? Because I used a different color for the other ones. So 45 degrees. What should we start with? Well, let's start with cosine. Cosine is the adjacent over the hypotenuse. So that's 1 over root 2. Used that one before. We've seen 1 over root 3. With sine, we've got opposite over hypotenuse. That's 1 over root 2 again. Very cool. And then if we're talking tan, it's the opposite over the adjacent, which is 1. And now you've finished, finished your table, and you can memorize this. Is that pretty easy to memorize? You can look for patterns. I personally don't do things that way. I'm not a person that works on memory. If you are, then use it to your advantage. But I don't work on memory. I work on solving problems in the moment and first principles, which means I'm going to be drawing these triangles using like the geometrical facts, if you will, and then building up my argument from there. At least you've seen it now, and there's your mini lesson. Okay, back to the question, and we can now always refer to that one if we need. Some people like to write that at the beginning of the exam. So we're going to find x, in this case label the triangle. So here's the angle of interest, we'll call it theta. We've got the opposite. And this one is the hypotenuse, and we know that because it's opposite the right angle, like that. And so we're going to write the most appropriate ratio here. We're involving the opposite and the hypotenuse. The most appropriate ratio is sine. which I'm going to actually write first. There's no harm in writing it first and then filling it out. In fact, we might need to move this a wee bit up here. Okay, fill in what we know. We can see sine 30 happening there. We've got the opposite, which is 20, and we've got hypotenuse, which is x. Now, if I do type in sine 30 in my calculator, it's a half. It's 0.5. It's really useful. If you're having to show where any of this comes from, of course, then you've got all this stuff down here. Looking at our table, we know sine 30 is a half. We can see it here. And so there you have it. Now, why would you worry about this if you've got a calculator, right? Well, sometimes if you don't even have an idea about what's going on, like for example down here, sometimes this question is absolutely nonsensical. Like, what does it mean in exact form? But anyway, this is just the idea that you could have a question here that turns into something really nice that you could do without a calculator. And how do we resolve this? Because of cross multiplication, or we can switch that around. So we have x is equal to 20 divided by 0.5. So x, which is not a curly x, so I see in the diagram it's a plain old x, is 40 meters. So this question was set up to introduce the idea that you have here in first principles derivation of those exact values, and then to put it into practice and see how, wow, it can be really useful, because the sign of some of these numbers is not great. Okay, calculate the exact area of an equilateral triangle with sides of 12 centimeters. Okay, so we ought to draw this thing. And we've seen it recently already that we have an equilateral triangle is special. We know quite a lot about this triangle. So I'm just going to go ahead and write everything I know. And we're going to calculate the exact area. Oof, there's a couple of ways, but I'm going to favor the area being equal to a half AB sine C. And this is a great opportunity to remind ourselves of this trigonometry technique of finding an area. You can, of course, go down the road of finding the perpendicular distance and then multiplying it, halving it. But we're going to go down this road and see if this is easier. I think you'll find that the other way is a bit harder because you've got extra things to do and then a calculation at the end. If you just remember this one thing, not only do you know it's a possibility in the exam, but rather than, wondering what to do, because you've got it in your memory, so you're like, oh, that's in my utility belt. It's actually quite elegant, because if you note, we have everything we need. The area is equal to a half times AB. So how do we set this up? Let's go for purple. We're going to focus on this angle here. This would be C. Yeah, let's use all colors. This here would be, it doesn't matter either side, but I'll just got to call this one B. And green is this side here. Now you notice that they are surrounding an angle, okay? So if I draw that in plane terms, it's the elements like this around an angle, the angle in the middle and the two sides that create that angle. And once we have that, they just go straight in. It doesn't matter which way around A and B are, even though they're the same here. Why am I writing 60 is 12? And sine of 60. Now we know from the previous page that sine of 60 is root 3 over 2. So we can just replace that straight away. And it says calculate the exact area. So we don't want any decimals. We want to leave it like this. A half times 12 is 6 times 72. So 100% got that correct, because 12 times 12 is 144, divided by 2 is 72. Okay, that's good. It's going to move it across. Actually, no, I'm not. I quite like to see the fact that this became this, and that this is in line here. Okay, so my final is going to be 72. So I'm going to focus on 72 divided by 2, because that's a fraction I can cancel. 36 root 3. And if that's not an answer that you're happy with, like looking at it, I'm going to show you what that is as a decimal. So 36 root 3, which is not correct because it asks us for the exact, is this 35382 blah 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 blah. Goes on forever. And this is obviously wrong, but this is correct because it's exact. And you can see, like, maybe you're less scared about the 62, but this is a more elegant form, and you write less, and it's exact. Why wouldn't we want the truth, eh? Not bad. Not bad. Okay. Sine x is 4/5. What is the value of cosine x? Well, you know, some of these questions I had to put in because I feel they're good questions. But I always found at your age, this question was so confusing. But let's unravel it a little bit. And first of all, let's not be intimidated. You see something different and you quake in your boots can be the worst thing you can do, right? So let's just rethink, what do we know about sine x? Well, sine x, like sine theta, is equal to the opposite over the hypotenuse. And it says up here that that's 4/5, like this. So if we did if we drew a triangle, like a right triangle, like so, and let's call this the angle x. That's the focus angle. The opposite would be 4, because that's opposite the angle. And the hypotenuse would be 5. And we can know everything we need about this triangle. The last side can be found with trigonometry, so Pythagoras. So we got 5 squared, take away 4 squared, square rooted. That's 25. Take away 16, which is the square root of 9, which is 3. So this bottom side is 3. I could have told you that before calculations because this is a Pythagorean triple. 3, 4, 5. But, you know, that's advanced mode and not what we're here for now. We've now fully completed the information on this triangle. And now it's asking us what's cosine x. Well, based on this triangle, we can refocus to the cosine formula or ratio. Cosine is the adjacent over the hypotenuse, which in this case, if the x is the focus, it would be 3 on top, and the hypotenuse is 5. So cosine x equals 3/5, and not a single calculator button was pressed. So in this instant, like in this case, it does count as an exact values question because we've not gone into that crazy realm of all the different decimals. And I'll go back to the beginning to show, if you type in, let's go down a wee bit. Sine 56. These are the crazy kind of decimals that we're talking about here. And it just goes on forever and ever. Isn't it really nice that some of them are a half rather than all of this nonsense? So instead of having to go through and calculate, we're just using nice numbers. Oh, hello. Somebody wrote stuff. Somebody wrote a lot of stuff. Let's see if we zoom out a bit here and okay, see what's going on. The diagram shows the roof feature of a skyscraper in New York. The angle of the roof needs to be at least 45 degrees to stop those darn birds from nesting. The base of the roof is 14 meters by 8. That's on the diagram. The triangular ends are isosceles triangles. Okay, so this would be the triangular ends. They're isosceles, which means that length is the same as that length. I don't know if that's useful at this point, but it's true. And the sides are isosceles trapezium. So this would be a side here. If they're the front and back, that must be the side. An isosceles trapezium is one where you've got two parallel sides like this, and the angle created here and here is exactly the same on both sides. So this length is the same as this length. It's sort of symmetrical down the middle. And that's what we have going on. And if you know, this angle is angular. I mean, you could have had a trapezium that did this, which is 90 degrees. But this has an angle away from going straight up, which means that this end triangle is tilted. Curious, Mr. Potter. Let's rub that out, not draw some more. The very top of the roof is 10 meters. What? You're confusing yourself. Is it 10? No, it's 9. The beauty of this is, I think I can adjust this. Hey, the very top of the roof is 9. I'm assuming the diagram's correct anyway, rather than the numbers in the question. And the length of PM is for root 41. Okay, we gotcha. We gotcha. Has this been designed well enough to stop the birds nesting on the ends of the roof? So how do we know this is a 3D trigonometry question? First of all, it's a 3D shape. And second of all, it's trigonometry because we've got triangles involved. They're probably going to be right angles eventually. And so that's the key indicators. And how is it different from anything we've done already, which is basic ratios? It's just, can you see the triangles properly? Do you understand this diagram? Like if it was a real thing in front of you, do you understand fully what's going on? I've already talked about how this here, if we went straight up like this, is not exactly there, right? In fact, if I draw a drop line straight down from here, that hits right there on the floor. And so there's a little bit of sort of a gap like this, where we have a right triangle, because it's not over the edge of the shape. It comes in a bit, it's tilted, and that's the same over here. It goes down to there and across. So appreciation for that visual is like paramount. And once we can see those triangles, you'll see my solution is just drawing 2D stuff. Has this been designed well enough to stop the birds nesting on the ends of the roof? Show all of your supporting working out. Okay, we can do that. So what we need to show, I think, is this, look, this angle here in the triangle. This is the tilt of the roof. It's the angle of elevation. So imagine this is the floor. The angle of elevation is what comes up from a horizontal floor. Okay, the angle of elevation is, let me do a different color so it's really obvious. We're going for the red angle, okay? I'm just going to make that really clear. So we're going to need some information. In order to find the angle in a right triangle, we need at least two sides. If we go back to the ratios, I'll just explain why. So looking at these here, in each of these individual calculations, there are 3 elements. And in order to solve, you need 2 of them. If the angle is the unknown, we need the other 2 sides. So going back to our question, to get this angle here, we're going to need 2 of the sides of that triangle it's in. So my first aim would be to draw that triangle, but flat. So I got something to work with. And I can label it if I had any points. This is obviously point P at the top. I could label this point down here as something not been used, call it A. So that would be point A down there. There's the right angle. And point B is the midpoint over here. Because it's the midpoint because there's an isosceles triangle. Okay, so essentially that's going to be 4 either side. Yeah, there's the angle of interest, and we want to find at least 2 of the sides of this, so call the angle of interest theta. And if we know what that angle was, we could tell if it's more or less than 45 degrees, right? That's the point. Yeah, 45 degrees. So let's get to work. Like I personally think that I've only got limited skills in the GCSE, so it's probably going to be something to do with trigonometry. So I'd be thinking, oh, what could I do? How could I find a right triangle? But whenever it does mention isosceles, where did it say that? Here. They often say that for a reason. And it's a very good skill to be able to think about an isosceles, as we've seen earlier today, as 2 right triangles. So I feel like that's the play here. Okay, so I'm just gonna draw that a little bit better down here. So hopefully we can see that this is this is point P, this is point L, and this is point M, and this is the slanted edge. What do they call it? End. A slanted end. And we're interested in this drop length here, because this drop length, this is what I mean about appreciating 3D, this drop length is the same as the hypotenuse of the triangle we're after. So you'll notice that this is B in the middle, this is PB, and our triangle, we might want PB. So let's label everything we have about this triangle and see where it takes us. There's root 41. We're going to deal with one triangle at a time with trigonometry. There might be other ways of doing this, but honestly, we only want that middle bit. We only want the right triangle part anyway. And we know this is 4. Hello. This is really weird. It's like there's a ghost controlling my... Oh, I can't even get rid of that. Where were we? We know this is 4. Because that's half of that. And so now we just need to work out what the missing length is. Now this is only sides, so we don't need to worry about trigonometry at this point. So the square root of 41 squared, take away 4 squared, is going to give us the length PB, which we so desire. Let's clear this up. I love it when it's a square root, because you square it and it's just the number. And we take away 16. Well, that's pretty good. 41 take away 16 is 25. So PB is 5. And we are measured in meters here, so maybe I'll do that once at least. All right, we're on our way. So we now find that PB is 5. So that's really cool. Got that there. And we need another length. I'm thinking there's a whole thing we could do with this triangle on the base to find this length, because we've got 4 there, but we don't really know any other lengths. So I'm not going to go down that road. I'm going to go instead look at the top. Now, because this is an isosceles trapezium, we know it's symmetrical. If the total length is 14 and the top length there is 9, that leaves us a difference of 5, and that's shared equally on both sides. So the gap BA, so just find BA down there, is equal to 5 over 2. Now you could write 2.5, but it's in your best interest to get used to fractions. Be comfortable with it. So here's 5 over 2, and that's just from logic. It's really useful. And that's meters. And we have everything we need now. We have, if this is the angle, this is the opposite, so that's not really going to be used. We've got hypotenuse, we've got the adjacent. And where hypotenuse and adjacent are given, then we're going to be using cosine. Typically would like more space than this, but well, let's try and squeeze it in. Cosine of our unknown is equal to the opposite, sorry, the adjacent, which is 5 over 2. Put it in a bracket because it's a fraction and it's going in a fraction, so I'm going to keep it as a thing. Like this. So this is the calculation. 5 over 2 divided by 5. Well, how do we think about that? There's a number of ways of thinking about that. My personal favorite is to go to first principles again and really think about what's happening and look at my fraction work. I'm dividing by 5, which is the same as multiplying by the reciprocal of 5. So I have that cosine theta is equal to a half. Now this is a point, I'm definitely going to get some more space with this point. In the exam you have the luxury of more space, but I here have the luxury of adjusting what I've already done. Let's move the whole thing, it's going to be awkward otherwise. And then back up you go, buddy. All right, I think everything is back to order from chaos. So cosine theta equals a half. There's a couple of ways of looking at this. The first one is, let's go back to our table. If cosine of something equals a half, when is it a half? Boing, 60. Or we can look at the numbers in here, 1 and 2, and think about what triangle had that in. It was the one, like, I'll show you with the equilateral, where we had the 2 there and half of that was 1. So we could think, okay, well, let's draw this triangle and then work backwards to it. But it's like the idea of going like backwards the other way. And I'm going to take a moment just to think about if there's any other way that would be pretty awesome. Perhaps not. Excuse me, I'm just going to cough. Nope, that's pretty much how I would do it. feel free to ask or suggest how you would do it if you had these, in a real elegant way. But if it works, it works. If you had a calculator, the only other thing I could say is if you're wondering what this value is, you would apply cosine -1 both sides. Like you're solving an equation. So you'll get theta. Because you don't want cosine theta, you want theta. So you can get rid of this cosine by applying cosine -1 to both sides, which will have you type in your calculator this. So you would do inverse cosine 0.5 and you'd get 60. So I'm going to leave it there because you do have a calculator exam coming up, but let's just say you're looking at this in 2025 because you're about to take your 2025 exam. I'm like a time traveler right now. Just imagining the years going by. Then, maybe this is in preparation for a non-calculator exam, which is perfectly fine. And then you have to have non-calculator methods. But anyway, coming back to here, we now know from a number of different sources that this is 60. So that's useful for us. But we have to make a conclusion. How has this been designed well enough to stop the birds? Well, clearly, yes. We just put that 60 is much more than the 45. Therefore, design, should we say, will keep the birds at bay. No, we don't want them at the bay window. We'll just say we'll keep the birds away. There you are. Okay. And the skill here is the worded part, right? A lot of people get put off by that. Just focus on a lot of the time these numbers will be in here already. But there you go. Look at that ability to draw in 3D. And I'm not going to take that lightly. I'm going to be feeling blessed about my ability to draw in 3D. Like the way I know that, this. I'm trying to think of a solution here to show you again, but yeah, let's just draw it again down here. So the way I knew that, oh, this is so frustrating. I wish I could just draw it again. I will. You know what? I'll do it on this one. Right, so the way that I knew how to draw this was through the rules of perspective. I know that if I've got a drop down, I'm going to go straight down until I get to here. But how did I make the rest of it look 3D? Well, I know that it's going to go halfway up this line, so it should be sort of approximately there. But there's a way of looking at it that all of the lines here, look at this line on the right, this line here on the left, they're all parallel. So any line going in that direction, like on the base floor, has to be exactly parallel with the other lines. Okay? Now it's very tempting to go down and then like that. Why? Because that's in line with the page. Yeah, like this page that we're writing on is perpendicular like this. But you need to go parallel to these lines. Okay, so you use those as a cue. And the same is true when you draw your wee little right angle. Some people do this. Look at my right angle here, right? It's like, I'll zoom in, it's like this. It's parallel with this page. And it shouldn't be, right? It should be anything going this way is parallel to the floor. And anything going down is going to be parallel to this down line, like this. And then I know that this point here joins up with that point with a straight line, so there we go. And now suddenly I've drawn this triangle in 3D using all these points of logic. That I knew it needed to go there, I needed it halfway across, they join up the straight line. And I feel really lucky that I'm able to draw those things. So next time you're asked in maths to do a lesson on drawing, don't scoff at it. These skills are important later on for understanding more complex mathematical situations. Anyway, there we go. Let's move on, and I'll adjust my microphone. Right, are we in a good place? There. 2 more to go. Great fun. A cube of wood with edges of 6 meters has a chunk cut away from one vertex as shown in the diagram. Oh, beautiful shape. It's like a right angle there. It's like a right angle triangular based pyramid or something. Angle ABC is 30 degrees and B is the midpoint of AF. I see that. It's all on the diagram. AD equals AC is not on the diagram, so AD equals AC. Is there a part B to this? Okay. There's just a part A, but, you know, it had to be a part A rather than the question. So let's just get rid of that. I think there used to be a part B. So calculate the exact area of the isosceles triangle BDC. BDC. Okay, so it's this thing here. And that's if the chunk's been taken off. That's what we're focused on. Okay, the exact area, you say. Time to label what we know, I suppose. So again, this is in a 3D trig or 3D something because it's a 3D shape. But I'm going to make my life a wee bit easier. Now, the information given to us in the question comes from this triangle I'm about to draw. ACB. Because we're given the angle ABC, which is here. Reminding myself, it's 30 degrees. And here's the other bit of information, I suppose. Let me highlight them both. That's the first bit. And the second bit is that B is the midpoint of A to F. And so we're reminded of this cube being 6 meters in all directions. So BF has to be 3. Which makes AB 3. That's the implication. That's the point. Okay, so this is really useful now. We're like really happy because we have all elements. Okay, we don't have all, we've got enough. We need 2 out of 3 and then we can find a third. So what do we have? We've got the adjacent. Here's the opposite and here's the hypotenuse. What would be nice to have? What would you want? Tough. Just trying to remember the way I did it in my head just now when I was thinking about it. There's a couple of ways of doing this. Like, I don't know what that angle is there. You can't tell what that angle is. So I'm not going to go down the half AB sine C. I'm going to go down the road that I want to find the length DC. And I want to find the height of the triangle. So I've got a couple of triangles that I'm interested in here. And I'm going to draw them. It's BDC. And I know that this is isosceles. So it can be taken down the side like that. Would be really useful then if I had the side BC, right? Because then I could start working with a triangle perhaps. And it's actually really useful that I have DC too. I'm just thinking ahead. Because if I had DC, I could work out what this side was, and then I could work out the length of it. So actually, I need it all. So let's just start with BC. So if we want to find BC, our focus is hypotenuse and adjacent, which is cosine. So cosine of 30 is equal to our adjacent, which is 3, divided by the hypotenuse, which we're calling BC. So we want to find BC. There's a wee trick here. When you have a number equal to a fraction as a statement, you can just switch out the number with the denominator and you'll still get a true statement. So that means that the cosine 30 is going to switch to BC. That's a little trick for you. And that sort of a trick is a good trick because it's only rearranging equations. It's a bit mindless. It's not a trick based on anything too difficult in terms of conceptions. So now we can have a look at this. Are we doing exact values or what? Look at this. We're going back to cosine of 30 is root 3 over 2. So we got 3 over root 3 over 2. And it was really cool to look at this as 3 times its reciprocal. Like this. And then BC is equal to 6 over root 3. Now anyone who's done work with surds knows that this is not simplified. It's got an irrational denominator. So if I multiply the top and the bottom by root 3, then I will get on the bottom 3 and on the top 6 root 3, and then 6 divided by 3 twice, so I'll get 2 root 3. And this is a wholly better number to be working with. I'm going to take the time here to move this aside, maybe to here. No, not get rid of it. But that's an important result. Okay, we're just going to highlight that because it is. So let's put it in our diagrams. BC is 2 root 3. What's next? It'd be nice to know the opposite. So the opposite is the sine, but we probably want to use the value we haven't calculated, the one we were given, which is 3. So in that case, it was going to be a tan. So tan of 30 is equal to opposite, which is AC, all over the adjacent, which is 3. We go back to our exact table. Tan of 30 is 1 over root 3. Within 1 over root 3, just like that. There we go. Over 3. So AC, let's keep it on the other side. AC is equal to, multiplying by 3, 3 over root 3. Hold on. Yeah, there we go. Right, so AC is 3 over root 3. Let's highlight that and then put it on the diagram. We're getting there, we're getting there. So 3 over root 3. We'll get rid of adjacent now because otherwise it's going to clog up our thinking. Okay, so we've got a lot of information about this triangle that's down here. And I'm thinking also we've got an interesting triangle on top that I'd like to draw. I suppose it doesn't matter which way around, but I'm going to choose to draw it like this. I feel like if it's somewhat in the same orientation, it's easier to sort of handle. This is triangle ADC. Take a moment to look at ADC. It's on the top, like this. Actually, not too sure if that's too important. Do I need to do that one? Yeah, I do, because I need to get to DC. Yeah, so what we have now is AC. So if we look at AC, this is an isosceles. AC was 3 over root 3. Like that. Fact that this is in the corner. So it's like a right triangle. So my diagram is really messing me over, ADC diagram, because this is not what it looks like. Right? So let's draw that a little bit better to reflect the diagram. Okay, so it's a right angle in the corner, like this. Oh, shape recognition should help. And this is the top, so ADC. A is a right angle. That's useful, right? Without that information, I had to resort to interesting methodology, and I didn't actually start it, or it could have got very interesting. But now, because this is isosceles, and we knew at the top here that AC was 3 over root 3. And that's 3 over root 3. We know that this is a right triangle. So we can find an angle here, which is going to be really useful for us. If this is a right triangle, that's going to be 45 degrees. Because it's an isosceles, right? And therefore we can find this long side, which is in all circumstances the hypotenuse. So we're going to pick a focus angle of this, because why not? It's going to involve the hypotenuse, and both of those are exactly the same, so we're going to go for the opposite. So sine 45. In fact, do we have a quick look? Oh no, they're both the same. Any advantage? If we use the 45 degrees, like they're both the same. The only advantage is we use tan, but that's not what we need at all. So yeah, no real advantage. It's both 1 over root 2. So sine 45, which is 1 over root 2, is equal to the opposite, which is 3 over root 3 over the hypotenuse. Actually, let's give it the letters DC. And that's 3 over root 3 again. Don't be afraid to write it twice. It's a good discipline, just to avoid mistakes and stuff. Switch them out because we have a fraction equal to a number situation. So DC is equal to 3 over root 3 divided by 1 over root 2, which is equal to 3 over root 3 times the inverse of that, which is root 2 over 1. So distances are getting pretty sticky here. I'll try and move this to a position that's a bit easier to work with. All right. So what cancels? Nothing much. Nothing much. This is 3 root 2 over root 3. We can do the whole square root of the 2 over square root of 3 thing and put it under 1. So the root of 2/3, but this is erroneous at this point. We don't know where it's leading so far. And all we can do is follow the numbers, and there's no need to put it in a calculator. You won't get any clarity here. If you put it in a calculator, all that's going to happen is you're going to get a decimal, and that's going to be even further from something where we can see the next step. So there's no need to do that. But I feel like this is possible if we know a little bit about surds to take it a wee bit further. So 3 is the square root of 9, isn't it? Yes. So 3 can be switched out, and I'll make that clear. 3 can be written as the square root of 9. Just like that. So that changed into that. And then that's the square root of 18, because 9 times 2 is 18. That's how surd rules work. And then that becomes square root 6. All right. That's probably easier to work with moving forward. So this is the root 6. Lovely. Not bad. Okay, looking back on where we've come. We now know that DC is root 6, which is this distance here. Let's draw a line. Let's get rid of that. We don't need that. This distance here, root 6, which means this distance is root 6 over 2. Lovely. What do we need? We don't need much more. This is really coming together. Now, just to remind, if we turn this purple, that this triangle here is our intended triangle. So we need to find the area of this triangle. So what do we need in order to find the area of this triangle is one more thing. We'll call it, what? I haven't used y yet. We'll call it y. We need the height. And rather simply, we're not going to use trig anymore. We can just use Pythagoras, because we have a right triangle where we have the hypotenuse and one of the small sides. So it's going to be 2 root 3 squared as the hypotenuse. Subtract root 6 over 2 squared, square rooted. That's equal to y. Love this exact value stuff, right? Square root 2 is 4. Square root the root 3. Square the root 3 and square the 2 is just 3. Just turns into that. And over here we square the square root, so it's just 6 over 4. We're running out of space. Let's give ourselves some, I hope, because we have yet to do the calculation for the area. And I so wanted to go through everything thoroughly as I could. We're at 12, take away 6 over 4, which is the square root of 48 over 4. 12 is 48 over 4. But the advantage of writing it like this is I have a common denominator. So now it's the square root of 42 over 4. I'm just deciding if I want to simplify that at all, but no, I think I'll leave it like that. So this is y. I'll write it as root 42 over 2. Yeah. And now to find the area of this triangle, finally, it's a half times the base times the perpendicular height, which is root 6 is the base, the whole of it, multiplied by the height, which is root 42 over 2. And what happens? We're going to take our sweet time. Wait, is there one more question? There's one more after this. Okay, so we won't take our sweet time. Let's multiply that in. That's that's 4. So it's root 6, root 42 all over 4. We're thinking, let's go in and then out again. So 6 times 42 would be, yeah, then 40. Yeah, I think that would work, right? So let's go in. Let's say 6 times 42 is 240 plus 12, so 252. And then we're thinking about numbers that will go into that factors. Sort of come back out the other side. We're looking for square numbers that go in, and I was thinking like 49. But that's not. It's not good. We're looking for a bigger square number here. We could do a prime factor decomposition that would help us. So 252, 2 times 2 is 4. I'm going to need to get that bigger. 12, 36. 36, 108. Yes. And then 7. I think that works. 108 times. No, this doesn't work at all. Two, 5, 2. That's 125, 126. 2 again. 63. Yeah, 63 is 6 times 7, so what on earth is going on? Am I doing that right? Half is 126. Half it again is 63. 63. Oh, no. 63 is 9 times 7. That's better. Now we're thinking about what square numbers we have here. We're looking for pairs of primes. So that would be 2 times 3. I can see that twice. If I just rearrange the multiplication, I can see I've got 6 times 6 in there, which is 36. So this is going to be root 36 times whatever was left, which is 7 over 4. Yeah, I'm pretty happy with that. So that's going to be 6. And then we can simplify the fraction to be 3 root 7 over 2. And that's an area, and all things here were measured in meters. Like that. So I'll highlight the final answer in a color I don't often use. Blue. Okay, we got there. Good job. So none of this was calculator, but it was all exact. Drink time again. But it's possible to get to here, and definitely to get lost. I missed that fact, and then we readjusted. Hopefully that that shows, not to panic in those situations. Okay, last question. The diagram below shows a pyramid A, B, C, D, P. Okay, with a square base A, B, C, D. Yeah. The side length of the square base is 2 root 2. Time to label, I think. And that's a square base. The vertex P is directly above the center O. Okay, so that's all centered. And the height PO of the pyramid is 2 centimeters. 2 centimeters. Okay, it's a small little thing, whatever this is. Let's do a drop from there. And that goes across like this. So we've got some like squares, I suppose, on the bottom. And then this thing here was 2 as a height. So I can already see some right angled triangles. For example, if I do a drop down here, I've got a right angled triangle in there. We don't know what we need. Let's press not to write too much because we'll clutter it. But that much is true. Okay. Calculate the exact length of AC, giving your answer in its simplest form. So AC is across here. This should go to that point. So AC is just about this triangle on the base here, which is Pythagoras. So we have the 2 small sides and we want the long side. So 2 root 2 squared plus 2 root 2 squared square rooted. Two root 2 squared. Okay, what do we got? We've got 4 times 2, that's 8. 8 plus 8 square rooted, which is root 16. Oh, nice. It's 4. This is all in centimeters. So we have our full length AC is 4. Let's write that properly. AC equals 4, 8 Yeah, 4 centimeters. Calculate the exact length P. That is very exact, isn't it? For calculate the exact length PA. Okay, PA is this hypotenuse, right? So this long line here, and this goes to the center. So this bit is the center of AC. So if we drew ourselves another little diagram where we had P at the top, O at the bottom there, and then A on the right. This base would be half of the 4, which is 2. The height we already been given is 2. And we want the length AP, or PA. So it's going to be Pythagoras again. 2 squared plus 2 squared, square rooted. That's 4 plus 4, that's the square root of 8. We'll leave it like that. Centimeters. That's the exact length. Because if you start writing this as a decimal, that's going to be not exact, right? Calculate the angle between PA and the base of the pyramid ABCD. Okay, so there's PA and the base. The base is along this line here. So the angle created between them is here. Call it theta. If we put it on our 2D diagram at the top, we know a lot more about this now. We know that's root 8. And we're trying to find this angle here. We're absolutely spoiled for choice. What shall we do? We'll probably go for tan. How did I arrive at such a conclusion? Well, if this is a focus angle here, then this would be the opposite. This would be the adjacent, and this would be the hype. But if I were to use the hypotenuse, it's a bit more awkward than using the whole numbers. So I'm just going to use the whole numbers. So tan, I know it's tan because that's opposite and adjacent. So tan of that angle is equal to 2 over 2. Tan is the opposite over adjacent, right? So 2 over 2. In other words, tan theta equals 1. Let's go back to our table. When is tan theta equal to 1? That's when the theta is 45 degrees. So, in this case, theta, because we want theta, we don't want anything else. We don't want tan theta, is 45 degrees, because it's true that tan 45 equals 1. So 45 was the missing piece there. That's what theta is. And again, if you want to double check that in a calculator, you would rearrange that equation by applying tan to the minus 1 to both sides. These effectively cancel out and you're left with theta. And you need to put this in a calculator, tan minus 1 of 1. And you will find that same result that we just got. Theta equals 45 degrees. Okay, therein lies our finishing point. Bit of trigonometry. We've revised quite a good portion of it there, and I feel like some of it mostly was problem solving. We've looked at the idea of exact values. We've looked at where we can derive them from, first principles, and seen them in the number of settings in 2D, in its purest form here, and in 3D, with a few other problems along the way, noting that keeping a handle on where we're at is important. And if at any point here during all of these calculations that we suddenly decided to convert to a decimal, we would not have arrived at our beautiful exact value at the end. Okay, so super important to be comfortable with a few skills. What do we use a lot of? We use a lot of surds, we use a lot of fractions, and BIDMAS, and rearranging of the equations, I suppose. But being very careful on our structure. And then we arrive at very typical question, pyramids. Pyramids can always be split into right triangles. Just be very careful about making assumptions. I didn't assume that it went to the center. It said in the question. But it doesn't always go to the center. The main reason it goes to the center is that it's symmetrical, but it's a square base. You have to consider where that might be if for example, it's a rectangular base and it was off to the side a wee bit. Like there. Like where does that hit down there? Maybe around there. And let's just say they draw it like this and it's not drawn to scale. Are you going to assume that it's in the middle? I think that's one of the most important lessons. We don't assume anything. We use logic to deduce, or we look at the facts that we were given. And that really is where a lot of people can go wrong with these sort of questions. Just deal with the information bluntly as it is. Awesome. Okay, it's we're at the end. We've seen all of the questions, and all that's left to do is to wish you the best of luck in your final exam and the exam so far. This is the one to play for. It's the last one. Best of luck, and see you on the other side.